record on this computer. So let's see, last time we stopped just before the topic of Lebesgue integration, which I'm just going to sketch. I'm not going to actually go through that in detail, although I think I have described it in words in a way that is explicit and more or less complete. So the basic idea here then of Lebesgue integration, I started to try to draw some pictures of it and wound up spending so much time erasing what I was doing that I eventually gave up. Let me see, I'm going to put this over here and I'm going to make this bigger. This damn thing keeps coming to block some of the space that I need to show you things. And I can get rid of this console for sure. So the first idea is about sets. And sets of points and sets of points being measurable. And so here I've got a set of blue points. And this is a very simple set. It just consists of 4 intervals. So we would say that the measure of that, oh, I'm sorry, it was the set of red points, 3 intervals. You see how screwed up I got making these figures. So here's a set of red points. And we can include all the points in 3 closed intervals, A1 to B1, A2 to B2, A3 to B3. Then the total interval AB consists of the points, the red points, and then the blue points, which are not in the set of red points. And we can put all the blue points in 4 intervals, C1, D1, C2, D2, C3, D3, C4, D4. And now what we see is that the sum here of the lengths, B1 minus A1 plus B2 minus A2 plus B3 minus A3, those are the lengths of the points in the space, in the set, and then the lengths of the interval not in the set, D1 minus C2, D2 minus, I'm sorry, D1 minus C1, D2 minus C2, D3 minus C3, D4 minus C4, the sum of those altogether, 7 intervals equals AB. So in that case, we say the set of red points is measurable. And I think one would say the set of blue points is measurable. So that's the idea of a set of measure. And the measure of the set of red points is the sum, in this case, of B1 minus A1 plus B2 minus A2 plus B3 minus A3. Okay. So now the idea then is, well, let me just mention a subtlety which may be a little bit scary. Suppose we have a countable set of points, namely just in the red set, instead of 3 being 3 intervals, is 59 points. Well, we could include those 59 points in 59 intervals, each of length 0. We would say the measure of that set would be 0. Anyway, the set is measurable if as you take the limit of more and more finely divided intervals, subintervals that cover all the red points, and the small and finer intervals that manage to cover all the points not in the set S, which are the red points. If the sum of all those intervals in the limit as their length goes to as small as we want, if that stays equal to B minus A, then we say the red set is measurable. And its measure is the sum of the lengths of the intervals, which might be smaller and smaller. And so Lebesgue applied that idea to an integral, and what he said was, you first of all suppose that all the values f of x of a function in an interval a to b lie in some finite interval in the y-axis. So in other words, we're talking about some interval here j, and we have an interval here a, b. And I learned earlier today that one wants to draw this thing very slowly like that. And then what we do is we imagine drawing. You see why this thing gets difficult. If you make the line too steep, then the intervals on the x-axis get very narrow. If you make it too the slope too low, then the intervals on the y-axis get too narrow. In any event, you see this is a set of points here that get mapped into this point, this interval, by the function f of x. And so Lebesgue's idea was, consider all the points j, and for each point xi, multiply f of xi by the measure of the set of points that f maps into f of xi. So in other words, here it would have been basically this value multiplied by this length. That would be one item, one term in this sum, and then another term would be this interval here. That would be m of s something or other that f maps into this interval there. And so that's the idea of the integral, the Lebesgue integral. You take the measure of the set of points that f maps into a value f of x I, and you multiply that value by the measure of the set. So in other words, it's a weighted average of the function, weighted by how many points get mapped into that value of the function. And of course, you might say, well, what's actually going on? What's actually going on here is that we've taken this, we have this interval a to b and this interval j that includes the image of ab under the function f, but we've divided j into these little regions, j1, j2, and so forth, and the same thing for the x-axis. So I think the better way to say it is simply in words, is that it's the weighted average of the function weighted by how many points go into each, how many x points go into f of a given point. All right, it's, maybe I should have just read this. In any event, the nice thing about it is that, of course, what we're doing is we're taking the longest, we let the length of the longest subinterval go to 0. And anyway, so one of the important theorems of measure theory is that if a sum f sub n absolute value squared converges, here we're summing from minus infinity to plus infinity, then there's a function f that's square integrable in the sense of Lebesgue, whose coefficients are this. The series converges to the function f, and the integral of the square of the function is equal to the sum of the squares of the coefficients. So that's basically something that lies behind quantum mechanics, because you see in quantum mechanics, you say your wave function is finite, and it can be the sum of the squares of the amplitude of the state of the particle being in the state, in the various n states. Anyway, Fourier series can represent a much wider function than just a set of class of functions than just continuous functions. So here are some quantum mechanical examples that, let's see, somebody said something in chat. Okay, well, let's see. As I said, I hope. All right, let's go. Maybe since there was a question here, I'll maybe go over this one more time, or in more detail for the first time. Suppose S is a set of point X that lie in an interval. All the points may also lie in several subintervals. Now what we do is consider all possible sets of subintervals that contain all the points of S. And we let M be the greatest lower bound of the sum of the length. So in other words, what we do is we're trying to catch all the points of S in a finite set of closed intervals, and then we try to do it in the most economical way possible. So we don't want intervals that have that include lots of points that aren't in the set S. So we go to the limit of the most economical containment of the set S into a finite set of finite closed intervals, all inside the interval AB. We can do the same thing for the set of points in the interval AB that are not in the set S. And now M is the most economical length, sum of M is the sum of the lengths of the most economical containment of the point of the set S, and M prime is the sum of the lengths of the most economical containment of the complementary set S prime. If M plus M prime is the total interval, we say the set S is measurable and M is its measurable. Is its measure. And in particular, every countable set has measure 0. As I said, you can include economically every countable set by just a set of closed intervals that start and end at each point. Each of them has length 0, and so the total measure of the countable set is 0. Okay, so what I'd recommend is that you read this several times if you want to fully understand it. Otherwise, it's basically just that the Lebesgue integral is the weighted sum of the function, of the values of the function f of x on the interval AB, measured by the measure of the set of points that is mapped into, that f maps into the value f of xk. or to put it more exactly, it's the measure of the set of points that F maps into a finite interval that includes the point xk. So anyway, it's just a different way of doing things, and it's you see the emphasis on the ordinary Riemann integral, the emphasis is on dx, and then you pick finer and finer dx's and you multiply each dx by an f of x that lies in the interval dx. So the emphasis is on the x-axis. In the Lebesgue integration, the emphasis is on the y-axis, and you're taking a weighted sum of values of the function weighted by the measure of the sets that are mapped into intervals containing those values of the function f of x. And you take the limit as the intervals get smaller and smaller and smaller. So it's intuitively clear. Well, I don't know about it. It's intuitively appealing, and it's clearly defined. And I think I clearly defined it in the description that is in the text that you have. So let's now go to the first quantum mechanical example, which is that of an infinite square well, of length 0 to L, and this is the potential V, and this is really going up to infinity. And so the particle is stuck in here, and it has to be basically, the wave function can be something like that, but it has to come to zero smoothly at 0 and L. And the simple answers are, you just take sine of pi n x over L. For x equal to L, that is to say at this endpoint here, x is L, sine of pi n is 0, and of course when x is equal to 0, the sine is 0. So you're satisfying the boundary conditions. These are smooth functions, and they satisfy the Schrodinger equation or Heisenberg equation, whatever. Anyway, the equation minus h bar squared over 2m. This is actually just p squared over 2m acting on psi. So it's the second derivative that pulls out pi n L over L squared. That's equal to En psi n. And the energy then of the nth one rises as n squared. And these are complete in that they span the space of all functions that are squareable on the interval and vanish at the endpoints. And these functions, these eigenfunctions of energy, provide a representation of the function f of x as a sine series weighted by coefficients. And so an arbitrary state, the general state of a function of a particle in this potential is the general wave function is of this form, where these are arbitrary coefficients whose absolute value is squared sum to 1. And at least if the absolute value is squared, it is sums to 1. I don't remember if I checked that. So what's the time evolution of this? Well, the time evolution of this is that it evolves according to e to the minus I ENT over h bar is how each psi n of x evolves, and psi of x and t then is equal to a sum over n of these things. And so that's, of course, the very general case. So in the first example, I picked at time equals 0 a particle confined to the middle half of the square well. So in other words, the square well is like this, 0L. And then this thing is confined between L over 4 and 3L over 4. And not only that, but the initial wave function looks like a perfect square of height square root of 2 over L. And so then the coefficients Fn are then the inner product of the state n, which is this sign with the this square interval. And let me change the color here. I'm getting tired of this black. They're the inner product of the nth eigenstate with the original state, which is just this square, namely this thing. And doing that integral, we find that the nth coefficient is given by the difference of two cosines, and it evolves in time in that way. The difference of the two cosines, the eigenfunction, the nth eigenfunction, and then the time evolution like this, En goes as n squared, and so the total time evolution is this. This is the general time evolution for an arbitrary state. If the SFNs are given by this square at time 0, the FNs are the coefficients at time 0 of this square wave, then how does it evolve? Well, it evolves as in the next figure. And let me get to that. Well, I've gone too far. There's the figure, and you see it's incredibly choppy. We can define tau as the time 2m L squared over h bar, L being a distance. And at time 0, the wave function is this thick curve, which is just these are all 1,000-term Fourier series. And so at time 0, the exact wave function is just the square well. The thick curve is the 1,000-term Fourier series, but at time 0. And so you see a Gibbs overshoot here. And all I computed here was not the function itself, but it's the absolute value squared, which is in order to get a positive number. That's why there's no Gibbs overshoot in the negative direction here. And so at time 0, the probability distribution of the 1,000-term Fourier series looks like that, with the overshoots. At 1/1000th of the characteristic time tau, it's the medium curve, which is this jagged thing, which is pretty bloody weird. And then if we go to the full time tau, it's the thin curve, which is really, completely crazy. Now, why is it that this is so jaggy? It's so jaggy because the initial wave function was not in class C2 or C3. It was in class C-1. That is to say, its first integral would be would have a continuous derivative, and so it was in class C-1. So on the other hand, what if we, instead of starting with a wave function that's discontinuous, what if we have a wave function that's continuous? And so I picked as the wave function sine of x minus L over 4. And here I said it was a C0 function. Let me just ask myself to check that, because I am just a little subject. This looks like it's infinitely differentiable, but maybe the point is that because it goes from 0 to a sine function, that maybe it is C0. I'll have to check that. Anyhow, we can compute the coefficients of this in, again, the sign, in terms of the sign, the eigenfunctions of the infinite square well Hamiltonian, and we find that they're 1 over n squared, and that's because, as I said, it's a function at time 0. The wave function is of class C0, which, again, it's not obvious to me that it's V0, but I think it actually is. That's what I printed. We can compute the Fourier coefficients, write the function, wave function at time 0 this way, where the fn's are given by this formula here, and then we can evolve it in time according to the energy eigenfunctions, which go as n squared. And now you see it's a much more reasonable evolution. It starts out as something that's peaked. This, again, is the absolute value squared 1,000-term Fourier series. This is peaked about the interval. Oh, and I picked capital L, I said equal to 2. So this is peaked about the original region 1/2 to 3/4. It's peaked about that region at time 0. Then as time goes by, it becomes a little less peaked, and you get subsequent peaks, but it doesn't have the crazy jagginess that the first example inherited from the discontinuities of the initial wave function. On the other hand, we can start with a smooth function. So here's a function that's actually smooth, and its Fourier series, in fact, has coefficients that are quite remarkable. They satisfy the upper bound 1 over n to the k plus 1. And the result is that the time evolution of this is much, much smoother, because the initial wave function was smooth. And you might wonder, well, how is it physically that the jagginess, that the discontinuity in the original wave function means that you get a jaggy time evolution? Well, the discontinuity in the initial wave function means that the initial momentum distribution had infinite terms in it, and those infinite momenta led to the jagginess, which in a sense brings us to Dirac's delta function. So as I said, the Dirac delta function is actually a continuous and linear map from the space of suitably well-behaved functions into the real or complex numbers. So if you consider it as a function, which it really isn't, it's of course incredibly singular. It's not only discontinuous, but it's infinite at one point, 0 everywhere else. But if you instead consider it as a functional, which is to say a map from a space of functions into a space of numbers, then it is continuous and linear. And the domain space is a space of suitably well-behaved functions. And different mathematicians have defined different spaces of suitably well-behaved functions. There's a Russian mathematician who remarkably, his name is Gelfand. He died maybe 5 years ago in New Jersey, actually. Gorbachev, who died on Tuesday, unfortunately, the age of 91, actually, because Gorbachev liberalized the Soviet Union. Gelfand went to the United States, and he, while in Russia and then while in the United States, he was one of the very few mathematicians who actually wrote so that people could understand what he was talking about. And his space of well-behaved functions were infinitely differentiable functions of compact support. That was one of his spaces. And he then took the trouble to explain to the reader explicitly and by examples how it was that you could have infinitely differentiable functions that were non-zero only in a, whose non-zero values lie within a compact, a closed and bounded set. In other words, you could have an infinitely differentiable function that was zero, did something or other, and was non-zero only in this closed interval. Anyway, I'm sorry to digress. In physics world, we write the Dirac delta function as if it were a function, and we say that f of y is the integral of f of x, delta of x minus y dx. And they pop up all over physics because, for example, the identity operator is an integral of outer products. F of y is the inner product of the bra y with the state f. You put in the identity operator, it becomes that, you get this. And so now you have this funny equation. F of y is something or other integrated with f of x. Well, that something or other, of course, has to be a Dirac delta function. And that is, so the inner product of these states that make up the identity operator, the position eigenstates, are that form then a delta function. If we use the Fourier series formulas, the function, or at least I guess its periodic extension, is given this way, and Fn is this integral of the function f. And so this integral dy is Fn. This e to the inx is just repeated. And so we can write it this way, that the periodic extension is of f is then this sum inside the parentheses, that is this sum here. I'm just rewriting this. On the other hand, these phases are periodic with period 2 pi. So we also have that f of x plus 2 pi L is this integral of the periodic extension of the function f of x times, when integrated with respect to this sum. And what is this thing? Well, it's an infinite sum of delta functions because it gives us f at any particular value here on the left-hand side. And so we can think of this as the Dirac comb. So the so this sum can be thought of as a sum of delta functions, which is thought of as a Dirac comb. And we can rewrite it in this way in terms of cosines. And I actually plotted it taking the sum of the first 100,000 terms in this cosine series. And I plotted it from -15 to 15 in figure 311. And so you see, you get a comb. This is a broadly toothed comb. So this is not really suitable for combing one's hair. One would have to make these less sharp, otherwise you'd draw blood from your scalp, and you'd want them closer together. But it's a mathematical comb. And now this can give us some more insight into and can lead us to Parseval's identity. So if we use the sum of the formula for the Fourier coefficients on a stretched interval, we can relate the sum of the products of the Fourier coefficients in this way. The sum of the products, well, Gn is this integral, Fn star is this integral, and we're summing them all. But now when we sum, we have a Dirac comb there. And so we get a sum of delta functions. And what happens when we finish doing the integral? We have a integral dx, integral dy, f star of x, g of y, Dirac comb. And that then gives us only one of them contributes, the one that's inside the interval from 0 to L, that gives us f star of x, g of x. And so the sum f star n, fn star gn is the integral f star of x, g of x from 0 to L. And if g is f, then it's the sum the absolute squared is the integral of the absolute squared of the function f of x. This, remember, was one of the relations that was derived rigorously from Lebesgue in the context of Lebesgue integration, which is the reason people like Lebesgue integration. This thing is called Parseval's identity. So if you have a function square integrable on an interval, the sum of the squares, the absolute value of its Fourier coefficient is the integral of the square of the absolute value of the function. Derivatives of delta functions. Well, again, they're delta functionals, not delta functions, but anyhow, the derivatives are simply defined so as to make integration by parts automatic. And if we keep track of things, suppose we wanted to solve x, f of x equals a, then the answer is f of x is ax over x plus bx times a delta function. And I see I'm running quite a bit ahead of schedule. My thought was that I would merely finish this chapter. And I see that we've already gotten essentially to the end of the chapter, or almost the end of the chapter. In fact, let me just check what we've got here. Yeah, we've only got a little bit more to go in this chapter. So one example or one application of Fourier analysis is to an actual physical string that is held at 2 points, 0 and L, and the amplitude then at any time y of t, y of x equal to 0, y at one end is 0 for all time, and y at the other end is 0 all time. In other words, it's if I switch maybe to colors here. So what we've got here is 0. Whoops, this is L. And so we've got a string that can, maybe I'll switch to blue now, a string that can do whatever, but is held down at these points. And typically, at least to a good approximation, it will obey a wave equation where v is a speed. And the solutions that satisfy this partial differential equation are sine of n pi x over L. That guarantees that y is 0 at the two ends. And then these guys, which are just cosines and sines, they're harmonic in t. And so the partial derivative here gives us just bangs out the original function. And notice the coefficients here of this and this have to be the same because we wanted to bang out the same function. And the space of functions that satisfy the boundary condition is spanned by these functions. And so we can use this integral formula to derive for any function, any shape of the string, like the crazy blue shape that I wrote, a Fourier series. The fn's are these coefficients, and this is the representation. And this, in fact, then gives us a representation for the Dirac comb here. Anyhow, periodic boundary conditions. Periodic boundary conditions are used all the time in physics because they're sometimes they're physically relevant, and almost always they're really convenient. In particular, we often have continuous infinite systems or continuous finite systems, and these continuous infinite or finite systems are intellectual nightmares, and so we make them much simpler by discretizing everything and turning space-time into a lattice, or turning a given interval into a set of interval divided up into points. And but there are cases where this is actually physically relevant, and in particular, if your physical system happens to be a loop, then indeed you certainly want that f of the end of the loop has to be the same as f of 0. And in fact, f of x plus L is equal to f of x. And here what we're doing is, I suppose I'm going to go a distance x here. And when I go all the way around, I've gotten to L. And then this point here can be labeled as x or x plus L. Anyway, of course, there are real physical systems that, to a great approximation, a high approximation, do have periodic boundary conditions, namely an actual crystal has a regular structure, and of course, I guess it's only an infinite crystal that's actually periodic, because the physical crystal, you come to the edge and it's no longer periodic. Anyhow, so what one does is one puts these conditions there: x plus or minus L t is f of x t. And in 3 dimensions, it looks like this, where these are any integers. See, this could have been any integer, the integer there. The eigenstates, the free Hamiltonian p squared over 2m, have wave functions that look, like this. And if we want periodic boundary conditions, then the momenta had better be, better satisfy conditions like this, or the momentum had better be one of these momenta. In other words, if P is 2 pi h bar n over L, then when x lies at one of the endpoints, one of the L endpoints, you have something like e to the I L, and then P is 2 pi h bar, say 3 over L, and there was an h bar that I left out, so this is e to the I 3 times 2 pi, and so that's equal to 1. So there's the periodic boundary condition. So then the momenta are restricted to these discrete values. The atoms of a perfect fistal are at the vertices of what some people call a Bravais lattice or Bravais lattice. I don't really know how that's pronounced. Anyway, these atoms are then some reference point, and they're just an integer times some vector A, which takes us a certain amount in the x direction, a certain amount in the y direction, a certain amount in the z direction. And the Hamiltonian for such an infinite crystal has to be invariant under translations that look like this. To make things simple, let's consider a cubic lattice spacing A. Momentum operator generates translations in space, and so we want the Hamiltonian to be invariant under this. And I think I should have written this as e to the I an dot p rather than exponentials. Let me make a 1, 4, 0. So what this says is that this exponential and h are compatible normal operators. And the first one being unitary, the second one being Hermitian. And so they can be simultaneously diagonalized, and we can choose the eigenstates of the Hamiltonian to be eigenstates of the translation operator with, or what is that? That will be, we can imagine the eigenvalue, we can choose the eigenvalue to be bin dot k. And then what we have is that psi at a displace point here is psi of x displaced by the unitary operator. This gives us the p acting on that gives us a k, h bar k, and yeah, let me look at that equation, 3.142. I am not sure. I think P was H bar K, so the H bar should have gone away here. And so that's a little silly, actually. So then what we do is we can set psi of x to be e to the I k dot x times u of x. And what do we need? Then this equation tells us that u of x must be periodic. And so the Born-von-Karman boundary condition then is that u of this is equal to that. And I must say this, one of the reasons, by the way, that one likes to use the summation convention that Einstein introduced, or a generalization of it. Einstein introduced a specific summation convention for special and general relativity, and because he got tired of writing sum signs. Obviously, this sum sign is so much bigger than x and n and a that we have to have these absurd parentheses. So what people really prefer to do is to omit the sum sign and just say whenever an index is repeated, it's summed over, and it's up to you to figure out what the hell the range of summation is. I'm now at the end of this chapter, and I think one of the things that I meant to tell you about, which is, let me switch again to blue. It's somehow black is so severe. Remember, I told you that the derivative of the step function, this is theta of x, and it goes here from 0 to 1 as, in other words, theta of x is equal to, this is the step function. It's also called the Heaviside function, And it's named after a man whose name was Heaviside. And the curious thing is that his name creates the definition of the function is a pun on his name, because the function has one side that's heavy. It has the value 1 all the way out to infinity. And on the other side, it has the value 0 out to infinity. So it's infinitely heavy on one side. So it's 1 for x greater than 0, 0 for x less than 0, and you can take it equal to 1/2, but for x equal to 0 if you want. And so what I said to you was that the derivative theta prime of x is delta of x. And I got confused trying to show you that last time. So let me now change colors and show it. And so let's consider an integral from -1 to 1 of, and what I'm going to do is I'm going to consider the derivative of f of x theta of x dx. And what is that? Well, that is going to be f of 1 theta of 1 minus f of 0, f of -1 minus 1 theta of -1. So that's just equal to f of 1. On the other hand, this is also equal to the integral from -1 to 1 of f of x theta prime of x dx plus the integral from -1 to 1. F prime of x theta of x dx. And what is that? Well, it's first the integral -1 to 1 f of x theta prime of x dx. And now if we do this integration, what we see is we actually, since theta is 1 from 0 to 1, this is really the integral from 0 to 1 of f prime of x dx. And so this is equal to the integral -1 to 1 f of x theta prime of x dx plus, well, this is just f of 1 minus f of 0. Okay, so now we want to summarize these terms. And so let me switch to green. And basically everything then, this whole system says that f of 1 is equal to this, is equal to all of that. And so that equation is f of 1 equals, starting from the right, f of 1 minus f of 0 plus the integral -1 to 1 f of x theta prime of x dx. Well, the f of 1's cancel, and so this is f of 0 is the integral from -1 to 1 of f of x theta prime of x delta of x, which of course is how we expect a delta function to behave, namely f of x delta of x dx across gives us f of 0. Okay, so that's what I meant to say yesterday, but the assumption here is that, remember when that mathematicians rigorously define delta functionals as maps from suitably smooth functions into numbers, continuous linear maps from suitably smooth functions into numbers. And and so the functions are suitably smooth. So so this f of x then would be I mean, we could imagine that f of x is a smooth function, so, which is, say, infinitely differentiable. It's sufficient here for it to just be in class C1, say, to be continuous, to have a continuous first derivative is all you need for this particular proof. But if one is rigorously talking about the theory of functionals, and in particular of singular functionals, then one would say that f would have to be infinitely differentiable, and some mathematicians would say that it goes to zero at infinity faster than any polynomial, or any inverse polynomial, or, as Gelfand put it, infinitely differentiable and vanishing outside some finite compact region. So did I answer the question? Okay, thank you. All right, so that was a good question. Now that I finally understood it. As I said, my hearing isn't great, and not every computer has the greatest, has the best microphone. And in fact, there was one guy giving lectures last week at Stanford, and either he mumbled or his microphone was so bad that I couldn't figure out what the hell he was saying. So I listened to his first lecture and did not tune in on the second one. So let's see, we actually have 15 minutes left. So I guess what we can do is start well, first of all, let's use the chat section from now on, because that obviates the problem of my hearing and your microphone and so forth. So if somebody has a question, please type it in the chat, and then I can try to respond to it. In the meantime, these complex exponentials, of course, are really great, but they're periodic with period L. And if we want to represent functions that are not periodic, then a better choice is to use real numbers rather than a discrete set of, in other words, a continuous real parameter like k, rather than a discrete real parameter like 2 pi n over L. And so let's sort of tiptoe toward that by starting with a Fourier series on an interval from minus L over 2 to L over 2. So we'd write it this way. And we could then write these, we could imagine that this f sub n was actually a function f hat of p, and we define f hat of p to be f of square bracket p, and square bracket p is the integer closest to the real number p. And so f hat of p is f sub n when p minus n is less than a half. And once again, you see that you have the advantage of the Lebesgue point of view, that you can basically ignore what happens on any countable set of points. And so we're ignoring the fact when p minus n is equal to a half, because then there'd be some ambiguity in defining f hat of p. So what we could do then is rewrite this as f hat of p, and we would be integrating it over a whole set of intervals. Here one would be integrating from n minus a half to n plus a half f hat of p, and we'd be summing over all n. And that then turns into an integral of f hat of p times this phase factor. And then the point is that this exponential minus the continuous exponential isn't very big, because square bracket p and p differ by only at most a half, and we're dividing by capital L, and we're going to let capital L go to infinity. And so this difference goes to 0. And so in effect, we can rewrite the function, the Fourier series, as f of x is an integral of f hat of p times this dp from minus infinity to plus infinity, e to the I px over L divided by square root of L. And we can now set p equal to k, we scale p to k multiplied by L over 2 pi, so k is 2 pi p over L, and then f of x is this, or equivalently this. And if we define f tilde in terms of f hat with another change of variables, it eventually becomes that f of x is equal to some other function, f tilde of k, e to the I kx dk over 2 pi. And now if we trace back what f tilde of k is, well, it's f hat of this, and f hat was defined as f of square bracket, whatever the independent variable is. What we then find is that f tilde of k turns out to be this. So this is remarkably symmetric. And so we then have the Fourier transform formalism that follows from the Fourier series formalism, as long as we, gosh, I can make this bigger, can't I? Should have done that earlier. Namely, that we can write a function f of x in terms of its Fourier transform f tilde of k as e to the I kx over square root of 2 pi. And then f tilde of k is f of x e to the minus I kx dx over square root of 2 pi. Well, the interval problem is gone, interval issue has gone away because we've stretched the interval from minus infinity to plus infinity. We have the square root of 2 pi's in a symmetrical way here. And if you're new to Fourier transforms, then you would want to use this symmetrical notation. If you've seen Fourier transforms a zillion times, then you can put the 2 pi's wherever you want. You can use equations like this. But the problem is when you use the asymmetrical notation, you have to be sure that you don't switch from the asymmetrical to the symmetrical, or from one asymmetrical to the opposite asymmetrical notation. So that's the opposite one. So one is this, the other one is opposite. And notice here I put in plus or minus. If you use a plus, then you use a minus there. So again, you're free to use plus or minus here, but you've also got to be careful. Don't switch, don't use plus in both cases, and don't change from using plus minus to minus plus in the same calculation. It's all right to use it on two different homework problems, but don't use two different conventions in the same problem. It's possible then to relate the Fourier series to the Fourier transform. And what we do is we sort of stagger backwards and say, well, f of x is this Fourier series. And we can write it also as this Fourier transform. And if we compare the two and keep track of all the definitions, we see f sub n is square root of 2 pi over L f tilde of k. So that's the relationship between this and that. And then what we can say is that the Fourier series looks like this, or equivalently like that. In other words, here's the Fourier series, and now we're substituting for the Fourier series coefficient, the Fourier transform function evaluated at k sub n. And going the other way, f of x is written as this integral. This is the Fourier transform of the function f of x, but we can use instead the Fourier series coefficient at a particular point here. And I should say, I think that one should sum these guys because implicitly we've got a sum there. Well, no, I think this is right. This is correct. This is okay. Well, we still have more time. I'm just completely surprised. Anyway, the most important Fourier transform is the Fourier transform of Gaussian, and so let's look at what it looks like in symmetrical notation. The Fourier transform of a Gaussian e to the minus m squared x squared over 2 looks like this. We then complete the square in the exponential, and by writing it as minus m squared times this thing squared over 2, and then this term squared gives us e to the plus k squared over 2m squared. So we compensate by writing e to the minus k squared over 2m squared. And now this integral here, it turns out we'll learn this in the chapter on complex variable theory, that this integral dx doesn't really care about the ik over m squared, and so we can rewrite it this way. It's a Gaussian, and then that Gaussian integral just gives us a factor, so that it's just a number. Of course, it's just a number. And the result is that it's e to the minus k squared over 2m, and the number is 1 over m. By the way, we already know at this stage that whatever this thing is, actually, we don't know that it's a number, because until we are sure that we could ignore the k, we don't know whether f tilde of k depends upon this the value of k in this integral. And in fact, it doesn't. The answer, by the way, is, the reason, just to skip ahead for a moment, the reason we'll find out that this k doesn't matter, it's that if you have an analytic function, then the integral of an analytic function along a closed curve is 0. And so if you imagine integrate, this is an analytic function of let me see now, how do I want to think of this? Right, it's an analytic function of z, where z here is x plus iy, and we can think of y as k over m squared. And so this integral tells us that we're integrating here over this line here at this value of y, k over m squared. And so since the closed integral vanishes, this integral is equal to minus that integral. And therefore this integral is equal to the integral along here in this way, in this direction. And then these two guys vanish because they're at k equal to plus or minus infinity. And there the value of the Gaussian is essentially 0. So that's what we'll learn there. And so what we find here is that the Fourier transform of Gaussian is a Gaussian. And what kind of Gaussian is it? Well, suppose m is very small, so that this is a Gaussian that looks like this. Very, very slow in x. It goes as e to the minus m squared x squared over 2. Well, its Fourier transform is going to be e to the minus k squared. So let me switch maybe to blue. Its Fourier transform is going to be very steep. It's going to be e to the minus k squared over 2m squared. So if m is small, so that this curve is very smooth. So let me switch maybe to green so if this curve is very smooth, then this curve is very sharp. On the other hand, if m is small, if m is large, then you have essentially something like this as e to the minus m squared x squared over 2. So this is for big M. Then the Fourier transform is e to the minus k squared over 2m squared, and it is very smooth. So this is smooth, and this is sharp. So what I'm stressing here is that the Fourier transform of a sharp function is a smooth function, and the Fourier transform of a smooth function is a sharp function. By the way, I checked using MATLAB, I checked that e to the minus 2 absolute value of x squared in that example that we did on Tuesday or Wednesday. And the one that I thought was very sharp, it actually is correct. It's that the scale goes from the x-axis is minus pi to pi, so that's 12, and the scale of the y-axis is 0 to 1, and so there's a factor of an order of magnitude difference in scales, so it would have been much smoother. Well, we're basically out of time. Let's see. Can I get? I said that I would meet with you guys either over the